Okay, so good morning, everyone. Welcome to one more Athena talk. It's a great pleasure to have with us a friend and a distinguished scientist, Professor Hilmi Volkan Demir. I will provide a short introduction to Professor Demir. He's a professor at the School of Physical and Mathematical Sciences of Material Science and Engineering at Nanyang Technology University, Singapore, and at the same time, professor of electrical engineering and physics in Bilkent University in Turkey. Professor Hilmi Volkan Demir established the Center of Excellence for Semiconductor Lighting and Displays at NTU in Singapore. And he has earned his PhD and master degrees from one of the most distinguished institutions in the world, Stanford University in the US, PhD in 2004, and his bachelor degree in 1998 from Bilkent University in Turkey, which is considered one of the most prestigious universities in Turkey. His work has received more than 19,000 citations, and his H index is 71. We are very happy and delighted and honored to have Hilmi together with us, and he's going to talk with us today about semiconductor nanocrystal optoelectronics for lighting and displays, pushing the limits and breaking the records. So the floor is to you, Professor Demir, and thank you again very, very much for your time and your contribution to our community. Thank you.
Thank you very much, Kostas. The pleasure is fully mine. I am very excited to be here with you, all my colleagues here. Let me share my screen. I believe it should be visible to you.
Yes, it is. Yes, it is.
And you can hear me well. Wonderful. All right. So once again, I'm Volkan Demir. I go by my middle name, Volkan, which really means volcano in Turkish. And my last name is Demir. Most probably you wouldn't know, but it actually means the element iron. So I am indeed the volcano iron. Something to remember, easy to remember. Once again, I'd like to thank the organizers, in particular Kostas and Talha, for their kind invitation. It's really great pleasure to be here today with you. And today I'll be talking about our research work on the development of semiconductor nanocrystal optoelectronics, in particular using colloidal quantum wells. This is actually my journey, starting with colloidal quantum dots and more recently moving to colloidal quantum wells for the purposes of lighting and displays. And in some cases, I hope I'll be able to show you that it has been possible to push some of the limits that we encounter in nanocrystal optoelectronics using colloidal quantum wells, and in some other cases, even break some records. Once again, I am from NTU Singapore, electrical engineering, physics, and material science engineering. And I'm looking after the center Luminous at NTU. At Bilkent, my alma mater, we have UNAM, electrical engineering, physics, and material science. With that, I'm very pleased to acknowledge the teamwork. What I will present you today is surely a result of all of this teamwork over the years. And this is Luminous. I'm working with a number of colleagues over there. Also, we have a fantastic team at NTU, including our scientists, research fellows, research associate officers, and students. And also, we have very close interaction with A-Star in Singapore. And similarly, I'm very pleased to acknowledge our team at Bilkent UNAM. We have a relatively young but strong and enthusiastic team there. And this is really the work of our group members currently and the past. You could immediately recognize Talha here, one of our alumni, who has been very successful After completing his PhD, he did a wonderful postdoctoral study at Cambridge, has been elected as Newton Fellow, and currently himself continue as an independent principal investigator and faculty member at one of the most promising and young universities in Turkey. And you may also recognize some of our previous group members. I am extremely happy and proud to observe our group alumni also continue their nice research work themselves. Today, I'll be talking about our work, particularly on semiconductor nanocrystals. And here, indeed, over the years, we started our work with quantum dots, then moved to rods, and most recently, for the past decade or so, we're looking into wells quite focused way, particularly because we can indeed exploit their unique properties for light generation and harvesting. In the interest of time today, I'll be able to talk more about light emission and lasing of these colloidal quantum wells. We actually also ongoing work on energy transfer and near field phenomena, particularly coupling with metasurfaces and other antennas made of dielectric or metal structures, functional media such as nanocomposites. Also taking materials into device level, we look into LEDs. I'll show you some examples from this effort. We are interested in making high quality, high efficiency light engines. These could be made 3 nitride materials, as we did work over the years and more recently, as well as soft materials. And this includes today's topic too, nanocrystals, but also perovskites, which I won't talk today. And within the last 5 years, we also developed interest going towards shorter wavelengths. This is now near UV and deep UV. Actually, we have great interest to develop chip scale solutions for deep UV in the UVC and far UVC. I'll today just show you one slide to share a recent example. We also like the idea of using ideas from optics and applying to RF domain, and this is about implantable metamaterials. We carry on research work on wireless in vivo sensing and wireless probes for other purposes. So given today's topic, let me share one slide very quickly, which is complementary to the work we carry out in the visible. This is now deep UV, and we have interest in solutions for low cost and large scale applications. And this is one device concept we came up with. This is the actual device fully fabricated. You can see it is several centimeters laterally and sub-centimeter thickness vertically. We can make at the moment 5 millimeters in thickness. And inside this device, what we have is high quality vacuum cavity. And in the cavity, we have nanostructures that are specifically designed to emit electrons efficiently under high bias, but low current density. So this device actually working under high bias, but using low current density requires low power. And with at least 4% and maximum 6% efficiency, we can convert these free electrons to photons. And depending on the cathodoluminescent material we use, we can generate the deep UV photons. So what we observe here is we can generate light in the UVC range, peaking at 265 with minimum 4% efficiency, maximum 6% efficiency. And we can have, as you see here, actually low temperature dependence. And as a benchmark, you can see in red here, the behavior of well-known mercury-based deep UV light sources, going high temperature, low temperature, significant decline in the performance, as opposed to this type of chip scale device where temperature dependence is profoundly reduced. So this is at the moment successfully commercialized with Sweden. This is Purify's formerly Light Lab. Currently, they are in the phase of large-scale production of these components. This is very exciting and interesting, and we surely continue this work. But today, I will talk about our work in the visible range. And this is really taking you to the recent examples of optoelectronic devices using colloidal quantum wells, also popularly nicknamed nanoplatelets. These are truly atomically flat structures. You can think of them as quasi-two-dimensional subfamily of colloidal nanocrystals. And here I'll be talking about their lasers, particularly using what we call all colloidal laser architectures. The interesting thing about these quasi-two-dimensional atomically flat structures is that they can actually provide record gain performance. So with that motivation, I'll take you through their advanced structures using them in lasers, LEDs. Also, I'd like to show a different aspect of such high aspect ratio materials having flat laterally and very thin vertically. We can think about orienting them in three-dimensional space. And we can put them all face down, or we can put them all edge up. This gives us yet another degree of freedom for us to make layered structures, again, face down or edge up or combination. And this is where I would like to talk about layered structures used in lasers and similarly in LEDs. Finally, I will just touch upon a new tool we are yet exploring, and that's doping before I conclude. I think this is well known to this audience. There is recent work within the last decade or so where we have been developing color science using semiconductor nanocrystals as discrete quantum emitters. And indeed, Talha, who's in the audience, together, we have been looking into this problem and understanding how we can create quality white light. Because previously, it was commonly believed that you need to have conventional continuous emitters. So the broad emission obviously makes it easier to generate white light. And this is the typical behavior using rare earth emission centers with many atomic transitions hosted in a phosphor material. This is the garnet, and creating very broad emission. The difficulty is with so many atomic transitions, it's difficult to fine-tune the spectral details. And this then manifests itself as limited photometric performance. On the other hand, if one would use discrete emitters such as semiconductor nanocrystals with the strategic combination, one can actually generate quite high quality white light with high photometric figure of merits. And that's the problem we have been looking into. This is obviously very exciting for solid state lighting, but also it has an important place in displays. And this is indeed the recent evolution of display technologies. Again, this audience is very familiar with the progress in display technologies, particularly using liquid crystal displays, where our focus has been to have large format, large area flat TVs and increase the resolution for the viewer. And in the process, making it low weight and slimmer was very important. But today, the focus has been shifted to generate high quality color experience. And this is indeed with the ambition to go beyond the nature. So to create hyper-realistic viewing experience. And this is actually possible using colloidal nanocrystals, again, as sharp emitters, starting with spectrally pure color components, makes it possible to span a larger color space. And in principle, even go beyond the nature if you can sustain the same color span plus the brightness you need. And with that motivation, Samsung, as one of the big players in the display sector, along with others, has been looking into making major investments. This is a recent announcement just about 2 years ago, pointing out that Samsung is committed to make investment of 11 billion US dollars over a period of time, particularly for quantum dot-based TV technologies. This is again where these semiconductor nanocrystals as quantum dots used for color conversion and enrichment purposes. And this is actually strategically important. And this discussion came out about a decade ago in the community where there was a strong comparison between this type of semiconductor nanocrystals and rare earth elements, which are not easy to find. Only certain geographical places have access to these elements. And indeed, this has at the time become a negotiation chip internationally. Obviously, as an alternative to rare earth elements, one can think about semiconductor nanocrystals made of 2,6 semiconductor group, for example, that are indeed widely abundant worldwide. And this was a point we made several years back, discussing that photometrically, we can also outperform this type of alternatives. And since then, we have been pushing this with colleagues and partners worldwide from academia and industry, both for lighting and display purposes. And recently, with that motivation and perspective ahead, we started an A-STAR program, which will keep us busy for the next now 4 years, where we have color conversion, LEDs, and lasing, along with colleagues over here, to generate nano antenna light emitting diodes using these semiconductor nanocrystals. I believe part of my colleagues here will be quite familiar with colloidal synthesis of semiconductor nanocrystals. I am happy here to point out that indeed, surprisingly, using such simple systems with quite low cost of initial investment, but then also low cost of maintenance and raw material requirement, we can create high quality crystal. Coming from conventional thin film epitaxy technologies, both molecular beam epitaxy and metal organic chemical vapor deposition techniques, MOCVD, indeed is always astonishing to me how high quality crystal we can generate over time, again and again. Having this type of low-cost solution-based material means also we can process them using solution-based techniques, again, quite cheap and in principle scalable to large systems. Also here, I find it important to acknowledge number of groups. This is really within the last more than 2 decades, almost 3 decades now, where a whole community together developed this high quality crystal synthesis routes using wet chemistry. And today, as we can control shape, size, and composition. We can fine tune to target specific extonic properties. And indeed, this is quite reproducible, particularly for the routes that are well nailed down, where we can hit the same peak emission wavelength or peak extonic absorption within 1 to 2 nanometer precision. And to me, this is a really excitement and indeed great success of the whole community. Plus, with certain chemical routes, again, we can have spectrally pure emitters with full width maxima shorter than, narrower than 30 nanometers. And some of the materials which are typically cadmium-containing ones have quantum efficiency more than 95%. In some cases, even near unity, limited with the precision of absolute quantum yield measurement. Obviously, this type of material is particularly critical to be evaluated for recycling purposes. However, in terms of the ppm requirement, it's actually a very low amount you use. So most of the time, it's okay to use them However, one has to think about the recycling issue. This property is somewhat not sufficiently acknowledged, and I believe it is important to be discussed, particularly because for rare earth-based phosphors, more of the time they're excluded because of the absorption properties and not the emission properties. To get the emission right is possible, but you need to get also the excitation bandwidth to match with your pump source. And most of them actually do not make this requirement because they have quite narrow absorption band. And finally, compared to organic counterparts in terms of photobleaching, photo and thermal stability, these material systems have made great progress. In my opinion, there is still more to go, particularly for high photon flux and direct excitation. In my opinion, increasing stability further will be useful. But at the moment, for example, for color enrichment in the black backlight units of TV screens, we have actually quite stable material systems, and one can think about combining different strategies if needed for further enhanced stability. So over the years, these nanocrystals we generated at Beacon and Singapore and TU have been used by a number of groups worldwide, and we are very happy to collaborate with colleagues both in academia and in the industry, and we truly continue to do more. These nanocrystals, along with colleagues, they looked into a number of applications. Today, we will just look at a subset of this large space of application domains. In particular, we will be talking about LEDs, but then also some of the lasers. And you see some of the work there, but they can be used also for single photon sources if designed carefully, solar cells, so light harvesting, bio applications such as biolabeling, tagging, and imaging. And this is just an example with Samsung we completed several years back, where not only for color conversion and enrichment, but also at the same time imparting polarization to the system as a critical property was the goal of this project. And here what we demonstrated is using spatial phonoresonances, we can actually suppress undesired polarization and indeed facilitate direct photon emission in a specific polarization we desire, as it should be in a liquid crystal display backlight unit. And this project has been successfully completed, and I'm happy to acknowledge our previous group members, Kıvanç, Burak, and Onur, along with ongoing R&D engineer Emre with us. So with all this happening, we were very excited and inspired by this work from CNRS, France. Our friends and colleagues there found ways to reproducibly produce these atomically flaked structures. And they demonstrated that one can actually have magic size vertically in a single batch. And this is, of course, important because the tight confinement is in the vertical direction. And we use significantly this quantum confinement while we can grow the structure laterally. So geometrically, we can make them large. Of course, one can do core, but as has been demonstrated, you can coat everywhere. So this is now isotropic growth, shell coating everywhere, particularly top and bottom, obviously the largest areas. But then you can choose to go for only an isotropic growth, which means one needs to extend only the lateral parts, therefore still keep the same starting vertical confinement. This was therefore for us a paradigm shift towards this optoelectronics of flat nanocrystals. And we were quite excited about this facility because now we can make structures lateral large while we keep the vertical confinement the same. Because in quasi-zero-dimensional structure, while we need larger particles to increase, for example, geometrical cross-section, thus absorption cross-section, we had to actually trade off with the quantum confinement. This is just a very simple geometrical argument. In the case of such quasi two-dimensional structures, we don't have to actually trade off with the confinement. We keep it the same, but make each particle geometrically larger. And this means we can still enjoy the giant oscillator strength coming from this confinement, while we can induce at the same time extraordinarily large absorption cross-section. And this is true both for linear and nonlinear absorption. So this was a very strong motivation for us to further go into optoelectronics of these colloidal quantum wells. Additionally, having this magic size allows us to also have quite narrow emitters. And indeed, for most of the chemical routes, we observed we are limited by only homogeneous broadening. So the external lifetime determines the absorption peak width, and in the emission is actually quite narrow, as I'll show you. Finally, as I already mentioned quickly, now that we have this quasi two-dimensional structures, we can choose to orient them in 3D space, such as face down or edge up, or alternatively, their combinations. This is one, I'd say, textbook example that I like showing, where you can see room temperature photoluminescence from these colloidal quantum wells. Quite sharp in emission. Here, full width half maximum is about 8 nanometers. And on the background in black dotted curve, you can see the absorption profile. These are heavy hole, light hole absorption peaks, extonic peaks result, and plateau absorption profile. This is pretty much a textbook 2D quantum structure one would expect. And this is, for us, an ideal platform to explore further. And this is the structure we utilize to see their gain properties with their absorption cross-section being high, both for linear and nonlinear regimes, and having their local density states to be large enough because of the very tight confinement, we expected to observe high gain out of these materials. And that was the goal, where we pushed this nanoplatelet film to go into gain. And using single photon based absorption, we were able to see successful gain behavior with the expected line width shortening, narrowing, and also expected integrated intensity versus influence behavior. Now, this was from core crown nanoplatelets as the first observation of gain from these quasi two-dimensional structures. Independently, I would like to also acknowledge my friend's work from Chicago, Dima Talepin, using only core in their case, where they were at the same time independently also observed gain. So this was quite exciting in the community, because it means if we have the single photon absorption, we should be able to get 2 photon absorption based gain too. And that's what we observed. In this case, we are using actually nonlinear regime. And to understand how this was possible, we also measured their nonlinear absorption cross-section. And we found per particle, it is over 1 million Goeppert-Meyer, which is extremely high. As a matter of fact, one of the highest we could find in the literature. This is good, and we need to obviously understand how this behavior compares to the existing colloidal quantum dot work. And in the similar times, in an independent project, we have been trying to push the lasing behavior using colloidal quantum dots as opposed to wells, using, again, this all colloidal laser architecture that I showed you, where the Bragg reflectors are also made of colloidal materials. In this case, titania and silica, titanium dioxide and silicon dioxide, as alternating layers, spin coated to create the Bragg reflectors, and then using pair of them to sandwich our gain material. And no matter how hard we looked into engineering the material, or the optical architecture, we always hit the limits. And these fundamental barriers actually came from the material, interesting properties of the gain material we used. These are conventional colloidal quantum dots at the time, the best materials we could find and indeed generate. However, the gain thresholds we were able to observe with them always were several hundreds of microjoule per centimeter square under pulse excitation, and not in the thousands range. The root cause is the gain coefficient is small. It's just 100 inverse centimeter. And this is accompanied by, as expected, ultra short gain lifetimes, typically shorter than 50 picosecond. And quantum mechanically, the limitation really comes from ERJ recombination. No matter how much we try to suppress this, eventually ERJ kicks in. At one point, we keep increasing the pump. Also, because these are quasi-zero dimensional and we need to keep certain size, absorption cross-section is limited. So with these fundamental limits in mind, one has to go to different strategies. In our case, our strategy was to go to colloidal quantum wells because we can make them laterally larger. We can actually have larger volume while keeping the confinement tight in the vertical direction. Another approach, as several other groups look into, making what is called giant quantum dots. Giant quantum dots, of course, there's still a trade-off, but ERJ you can reduce significantly. In our case, we had been looking into pushing the gain performance of these quasi-two-dimensional structures, and over the years, obtaining higher quality crystals and indeed going for higher pump. Here you can see we pump harder and harder. We can keep increasing the gain coefficient. This is variable stripe length characterization to demonstrate the gain capability of the material. And in terms of the model gain, this is basically the intrinsic material gain in the optical mode supported. So it is gamma, the overlap integral of the optical mode supported in the gain film, times the material gain itself. We can exceed 5,000 inverse centimeters. Here you see the spectral behavior of these net model gain. If you'd like to put this in a perspective, given the best reported values in the literature, this is for organic dyes, polymers, colloidal quantum dots, rare earth doped fibers, epitaxial quantum wells. These are all at room temperature and the best in their classes. We see that room temperature, they can only achieve certain level of peak model gain, as opposed to this very promising group of materials. These are all cadmium-based, cadmium selenide, colloidal quantum wells of 3 monolayers, 4 monolayers, and 5 monolayers, all again room temperature, providing higher gain. Possibly. And to make it fair comparison, these are the best numbers we were able to find in the literature. This is bulk gallium nitride at cryogenic temperature 2 Kelvin. And this is also another very promising material system we have been exploring ourselves too, perovskite. This is bulk perovskite, again, at reduced temperature. So this level of performance given at room temperature with no active cooling actually looks very exciting. And with that idea, just coming to our most recent work, we have been combining these two strategies, colloidal quantum wells, quasi-two-dimensional, make it laterally large, but at the same time, make it giant. So here we are pushing extremely thick wells for relatively for what we can do. And what we achieve now using what we call this giant colloidal quantum wells. And in terms of volumes, these are several orders of magnitude larger as a whole volume, extonic volume, compared to the so-called giant colloidal quantum dots. We can push the gain further and further. These numbers are extremely large and only possible with significantly increased shell. And these shells, you should remember, we actually coat everywhere. So with, for example, 5 monolayers of shell coating, we are actually increasing to make it 10 monolayers additional coating. And what we observed is there's a sweet spot where we can achieve the highest. And we were able to confirm this using variable stripe length characterization and transient absorption characterization. And we would like to push this further and use this very promising material systems again for gain purposes. Now, I'd like to change gears and take you to another research direction where we intentionally devise heterostructures. And these are different varietal architectures. Actually, it is very rich. One can think about and come up with a lot of different ideas using the concept of alloyed composition tuning, thinking about combining different heterostructures, in this case, not only core crown or core shell, but having the whole thing together, which means it is like a platelet in a box type of architecture. One can also look into electronic band alignment, type 1 versus type 2. We can tune the band offsets and even use the geometry to our benefit, although it should be actually type 1 band alignment with the right geometrical structure, we can induce quasi type 2 behavior. So one can think about using different combinations of these, and that's exactly what we did over the years. Looked into alloyed core structures. We could actually reverse geometrically where we will confine electron Hall wave functions and generate what we call inverse type 1. This is the early work we did. These days, we can make it very well defined, quite regular structure. It looks like a quantum ring. So we can confine in a donut type volume the both electron and Hall wave functions at the periphery of the particle. Type 2, again, alignment is possible. And what I'll show you is this particular architecture plated in a box where we combine the two strategies to create core crown shell architecture. I won't go in the details of this. This can be looked into further if anyone is interested, but studying core size dependent optical gain, core size dependent optical, crown size dependent optical gain, and spectral tuning behavior, type 1 versus type 2 based optical gain, and particularly this, again, plated in a box architecture, which is the most promising as expected. In this type of architecture, as we found out, it turns out that hot injection shell growth is very critical. This is a very well-known technique for colloidal quantum dots. But at the time, we didn't have a solution for this type of hot injection-based shell growth. And this was particularly important because either we do core shell or we do core crown shell. And at the end, we actually complete the structure with a hot injection shell material. This was critical to achieve high efficiency in terms of quantum yield, but also high stability against increased temperature during operation. And using this technique, in this case, we were interested in developing cadmium zinc sulfide based shell. We were able to observe very reproducibly high efficiency. This is really limited by our absolute efficiency measurement approach and has been indeed cross-checked with number of independent labs. It's near unity. We can see in this mono-exponential decay too. If we are to very rigorously wash these dispersion material, even then we can actually sustain high efficiency in the range of 95%. If you make films out of these materials, which means we actually confine them together in a small space in the proximity, there would be a homo energy transfer. And that transfer is a great penalty for us for the exton non-radiative decay. And in that case, in the glow box, we can achieve 87%. If we take this out into air, it's 75%. This is without using any barriers. These days, we can do better than these. With additional barriers, we can actually sustain, again, quite high efficiency using these materials. So we were excited about this possibility and have used it for a number of recent applications. This is for lasers, and this is for LEDs. And in the case of lasers, we generated a microfluidic channel. This is a chip we developed in the group, specifically designed to also contain a parallel pair of mirrors on the facets of the chip. This is simple Fabry-Perot type of cavity. And this is all in solution. This is a real image of the channel. And this channel has only the core crown gradient alloyed shell. This shell actually has hot injection growth, as we would like to. And with this type of solution-based medium, it's very difficult to induce gain at reasonably low thresholds. However, if the gain material itself has high gain coefficient, as should be for this specific engineered, highly engineered colloidal quantum loss, it is possible to reduce that threshold. And this is what we observed ourselves. This type of colloidal quantum loss gave us a threshold, which is 3 orders of magnitude lower than the best reported values in the literature. This includes previously the colloidal quantum dots, the dyes and variety of soft material options and molecules. This is really truly coming from the material itself. One can look into further in details for their lasing behavior. We wanted to do better than that. And up to now, I talked about core crown shell structure, but what we can do is we can alloy this shell carefully. And in alloying, we can generate these soft transition barriers. We carefully quantum mechanically calculate these, design, and then implement such that we have the highest gain capability. And indeed, in the ensemble, with this type of core crown alloyed shell colloidal quantum loss, we were able to observe in the film, this is now solid state, a sub-single exton level for the threshold. Still, we have biexonic gain. Statistically, obviously, part of our colloidal quantum wells in the ensemble actually pushed into a population inversion with 2 number of extons per particle, but it suffices to use only part of them in the ensemble. And on the average, because we are using only part of them, per particle of the whole system in the ensemble, we can actually have sub-single level of threshold. This was then the lowest gain threshold possible to observe in the film in solid state, thanks to, again, both this quasi 2-dimensional structure, shell group, but then having an alloyed structure. Of course, one can expect this type of material should also correspondingly have high stability under very strong pumping as seen here. And you can make also, for example, vertical cavity surface emitting lasers, as we have done in a vertical DBR structure using a pair of them. The same material, so again, highly engineered for the reasons I explained, but now a different use. And this is in a LED structure where we electrically directly drive these emitters. And we were interested in seeing high efficiency, and this was 19.2% at the time. This is the hero devices, the best values we could measure using the same colloidal quantum wells, again, based on hot injection shell growth, as I explained thus far, but having fully conventional structure. To be able to reach this level, we had to understand also the lateral structure, because in our synthesis, we can carefully make high aspect ratio, rectangular light versus squarish structures, and we have good control to do that. What we found is for this electrically driven LEDs, one has to go to low aspect ratio structures, and then we need to take that and again, look into a particular shell structure to achieve the best performance. Here you can see histogram of the devices we make. This is the hero device. I told you about several of them, 3 of them here, but the distribution is there. And actually on the average, we can achieve a value around 15%. But this number, hero device, considering 20% is theoretically the maximum possible value, puts this type of colloidal quantum well-based LEDs on par with those LEDs we make using colloidal quantum dots. Obviously, dots, our group and many other groups worldwide have been working for a very long time to achieve highest efficiencies. And with this type of engineered colloidal quantum wells, it was able to get the same level of performance. Given the time I have left, I'd like to now also show you another research direction we have been very passionately following, and this is orientation control. This is now after synthesis. We have these materials available to us, and we are interested in making films with proper control, assembling them in a specific orientation. Normally, if you don't have this intentional technique, you would have typically a mixture. You would have face down, edge up, and this is what would look like on a TM grid. You can see the edge up from the side, quite stacked like this in a chain structure. You can also see here, as I show with my pointer, the individual face down orientation. We'd like to have either, and this is the approach we develop using subphase. This is actually interface of liquid with air. This type of technique is well known for a large variety of organic molecules and other type of inorganic, organic nanoparticles systems. And here we have to develop this particularly for the colloidal quantum wells. And what we found is using a specific subphase, we can favor the orientation of these nanoplatelets at the interface, face down or edge up, a single phase. And then simply draining out the subphase, we can essentially work with on any substrate. This already aligned monolayer of nanoplatelets would simply sink in onto these structures. And this is one example where we very densely edge up, stack these nanoplatelets. This is also very important because in certain functions, we want them to be as close as possible. Now, one can also think about repeating these deposition steps sequentially to build up a structure you desire. Here, we have been interested in developing all face down and many layers together. This is a cross-sectional view. This is top view. Basically, one has to repeat the process with obviously some additional adjustments. And what we observed and the maximum we got was 15 layers. One can actually build up this type of face down slabs of the colloidal quantum wells. And this was interesting for us because we would like to understand the game behavior as we build up these structures. In a construct like this, we observe there is a sudden jump with which we observe gain. And that was important for us to explore because eventually we'd like to make them thinner and thinner if possible, and yet still induce gain. This is just a demonstration for 11 monolayers. Going up to 15 monolayers, the increase in the film thickness is linear as expected. We did not observe up to this point any significant outlier, and roughness still stays within a few nanometers range as it should be. And this roughness is particularly critical because if we have very rough surface, it means we will have strong scattering to outer half space, and observing amplified spontaneous emission will be very difficult. With this technique, we observed only with 6 monolayers and beyond, we can have gain. Directly on quartz, for thinner layers, there is no way to observe gain. To understand the reason, we looked at it numerically, and what we found is, as expected, with quartz and so thin gain medium and no spatial optical design, we have a very strong optical leakage into the substrate. As a result, the overlap integral of the supported mode with the gain is very low. Indeed, going from first monolayer to the fifth monolayer, it is practically zero, very low, in the range of 10 to the power minus 8 to 10 to the power minus 7 range. And then with the sixth monolayer, there is a sudden jump, explaining the reason why experimentally we observe an onset of gain. And going beyond, as expected, we get only better gain performance. With this understanding, we wanted to see whether we could push the number of monolayers beyond which we observe gain. And in this case, now to use additional assisting films, for example, on fused silica titania with higher refractive index, allowing us to better confine the optical mode in the vicinity of colloidal quantum glass, we were able to see, yes, we can do better. For example, we can have 2 monolayers to observe gain instead of 6 monolayers using such structure. And one can quickly think about using single titanium layer, which would be good enough to help increase confinement, or can do even more symmetric structure. But remember, still we have air on the top and fused on the bottom. So not purely symmetric, but closer. And this was the way we approached to have a thinner layer. And the thinnest in this case we achieved was, again, 2 monolayers. This is a 14 nanometer thick gain medium to observe, again, lasing behavior. I will spare you from the details, but tell you this requires obviously careful optical design and numerical solution and experimental demonstration to see this type of ultra thin gain material. And easy way to further push this, and possibly using only 1 monolayer, is to have even better cavity structure. This is very simple, again, a pair of Bragg reflectors where we sandwich single monolayer. And this structure itself only then allowed us to observe a single mode lasing from a single monolayer, which is just 7 nanometer thick. This is, to the best of our knowledge, appears to be the thinnest gain colloidal medium at the moment to observe gain. We keep pushing this in active device platform too. Given my time, I will just quickly touch upon before I complete. This type of structure now, again, oriented colloidal quantum glass, but in a device architecture. So one has to develop the compatible technique to be able to do this and yet obtain a working device at the end. This was important for us because with this type of proper alignment, actually we have the transient dipole moments in the plane, and this indeed increases our outcoupling. Where we have spin-coated, indeed the dipole moments are all over the place, randomly oriented, and this indeed limits the outcoupling. So this is a comparative study, again, self-assembled, face-down oriented nanoplatelets film. And this is the spin-coated version, everything identical except for the assembly. And in this case, as one would expect, we can achieve, this is experimental result, 92% in-plane, properly in-plane transition dipole moments, as opposed to the typical randomly oriented, and in this case, 67 experimentally observed of in-plane transient dipole moments. This, as a result, increased our efficiency to 18.2% using all solution approach. The best reported previous result is indeed below 10%, in the range of 7 to 9%, when you don't have this orientation. So this technique, we believe, could be quite exciting to make future devices too. Bringing me to my last topic, quickly touch upon, and I won't spend too much time on this, just to share with you, this is really at the moment in baby steps, in my opinion, for doping. Colloidal quantum dots for doping has been widely exploited. There is a very fascinating and encouraging literature, but for wells, this is quite recent. And we, over the years, looked into doping with copper. One can think about different chemical routes to do that. And this is interesting, for example, for luminescent solar concentrators. So this is now harvesting application as opposed to light emission applications I have thus far talked about. But with dopants, one can impart additional properties such as magnetic properties. And this is also something we are excited about, in particular manganese, because different than colloidal quantum dots, in this case, we have monolayer precision. So we can choose these dopants to interact, especially with a targeted part of electron or hole wave function. And this type of high precision wave function engineering, we believe, is exciting to explore. As I mentioned, just to complete my discussion here, this type of luminescent solar concentrators actually provide high performance compared to, for example, quantum dots one can have. In this case, obviously, the stock shifted emission works in our favor. Now, given my time, I think it is the right moment to conclude. I hope today I was able to convince you that colloidal nanocrystals actually enable high performance color platform, both conversion and enrichment purposes. And as the most recent subfamily of semiconductor nanocrystals, colloidal quantum wells also offer excellent gain capability. And orienting them, this is something new for us in the colloidal world, could be an interesting way to go to make particularly active devices. Finally, although we are at the very beginning, I believe doping is a great tool to further engineer these colloidal materials. With that, I'm very happy to acknowledge our funding sources, both from Singapore, Europe, and Turkey. And also, if there are those young researchers in the audience, we are happy to have indeed positions for you, both PhD and master level. Also, we are happy, very happy to host colleagues as visiting scholars if they have interest both in NTU and BCAN. With that, I'd like to thank you very much for your time and interest. Thank you.
Well, we are the ones who should thank you, Volkan. That's really impressive.
Oh, thank you.
Not only for theoretical reasons, but also since they are so, all these are, have all these wonderful technological applications, right?
Thank you. You're very kind. Thank you very much. I appreciate it.
So now it's time for questions from the audience. Does anyone have anything to ask Volkan or comment? Let me mention some things. I must say that this is not my field, but I understand that you are mainly concerned about layered structures. Is this because simply that you want to use these things in screens and things, or is it also because of the effective dimensionality, which plays some more, deep theoretical role?
A great question. Actually, there are different aspects, and it very much depends on what the final intended structure is. I can, I think, answer this question in a few different views. One is just passive optical structure. When we properly orient them, for example, face down, Quantum mechanically, we have strong confinement of transient dipole moments in the plane. And as a result, having them aligned all properly and not allowing them to randomly position themselves, it means their emission will become more directional. And you can think of these all independent emitters now for the first time with proper alignment. So as an ensemble, as a result, we will have better outcoupling. This is true for any optical film we use. Of course, now, if you take this very much same structure and place it in an active device, this means, okay, enhanced electroluminescence because of the outcoupling, but some additional property also emerges. And this is now the Hall and electron injection, so charge injection. When we have randomly oriented, we always end up undesirably leaving with pinholes. And in a continuous film, it is those weak points that determine the overall performance. With current, with electron and hole being injected into this active layer, they will tend to choose the least resistance pathway. And one single pinhole actually can kill the overall performance. Now, with this face down, actually, we are able to bring them closer and closer, leaving as little pinhole as possible. Obviously, never ideal because it's a statistical process, but then doing better than random oriented. And today I didn't have time to share. Also, our results are quite preliminary at the moment. We are looking into reproducibility, but you can think about doing this also edge up, because edge up, we can actually bring them further closer. So in those systems, it also is about how well current you can pass through and how much of those charges make into the actual emitter. Because in an active device, we pass the current, but not all of the charges actually go through the emitter. And as I mentioned, any pinhole, they'll find a way to go through. So there are different aspects. I just wanted to compare two passive optical structure and an active optical structure in terms of the assembly and orientation.
Thanks a lot. Does anyone have a question? Because I have some more. Yeah? Yeah, please.
Yes, hello. My name is Denis Donlagic. Very nice presentation. Thank you very much. I would just like to say that we are a group that we are working in a field of optical fibers and optical fiber microstructures, and I see a lot of potential maybe to merge some of this work and come to some certain devices. If you would be interested, maybe we can discuss this later on.
Yes, absolutely. This is very exciting. I believe there are a lot of possibilities to use together with fibers. Fibers are great platforms to integrate such gain medium. Absolutely, I'll be very happy if you wish to talk offline and see possibilities.
Yes. Thank you.
Thank you.
Very good. Anybody else? I would like to ask you something additional, please. You refer to the Auger process. And since I had worked on this process a long time ago, at least in my terminology, this is 2x. This includes two excitons colliding, and the one recombines, and it gives it ionizes the other.
Yes.
Is this the traditional Auger process, the way that I know it?
Yes, this is exactly a three-particle process: 2 electrons plus 1 hole, or 2 holes plus 1 electron, where the excess energy is given the third particle. And this is really limiting factor for gain capability of all these colloidal nanocrystals, both dots and wells. In the case of wells, one intrinsic benefit is that because we have causes two-dimensional structure, no confinement in the lateral dimension, this excess energy can be given to these free charges as kinetic energy and not necessarily go into Auger process as a non-radiative decay. In the case of dots, because of the three-dimensional confinement, this is impossible. Therefore, colloidal quantum wells have one step ahead of the dots because of the geometrical reason. But then the dots, one can do better too, because the Auger process obviously is more complicated than what we are just now discussing, because it also has to have the energy matching and transfer when the momentum conditions are right. And when you have these structures with these ligands, these are slopy molecules, actually there is scattering coming from them too, making this type of Auger process easier because they can then have the momentum requirement better satisfied. But if you move them apart, you reduce this additional effect. This is also true with colloidal quantum wells. Of course, we have the lateral dimension, which is free for charges to move, but we still have the bottom and top layers with, again, these slopy molecules, making easier to get the momentum matching to work. So if we can push them further apart, that coupling becomes harder and we further suppress Auger. From our experience, Auger always kicks in. The question is how far you can push it, because at the end of the day, it's a three-particle process and it grows faster. Of course, very small at the beginning, but you crank up the optical pump, eventually it will catch up. If you can push that point further out and have your threshold lowered, you have an operating window within which you will have efficient gain behavior. So that's what we are looking into doing.
Yeah, great. Thanks a lot.
Thank you.
Okay, in the chat, I don't see any questions. Some people right here,
yes,
are thanking you.
Well, thank you all back. And I see some of our also alumnus, Professor Zeliha Soran Erdem. Great to also hear from her and all other things. Thank you very much for your nice comments. Thank you.
Okay, if I don't know if there are any final question. Well, otherwise we should thank you again, Volkan. Great stuff, and we wish you the best for the future also.
Thank you, my pleasure, and hope to see you again.
Yeah. Okay. Yeah, and when you visit Crete, please.
Oh yes, I would love to.
Yeah.
I would love
okay.
To.
Okay.
Right. Thank you.
So thank you. Thank you.
Very
Bye,
good
everybody.
day ahead and weekend. Bye bye, everyone.
Thank you. Bye.
Bye.